Hi, and welcome to this next video where we continue our study of learning theory, in particular in the setup where the hypothesis set that we're using is of infinite size. So in the previous video, we looked at the so-called growth function, right? So the growth function was defined as, it says here, this m sub h of n. It's the maximum over all n-sized sets of training examples of the number of different dichotomies, so the number of distinct ways that the hypothesis set h can label these endpoints. And then we saw that these generalization bounds, the one that we had in the finite case, could also be generalized to infinite hypothesis sets by plugging in this growth function here, evaluated at 2n, right? So we can say that the probability, where the probability is taking over a set of n training examples, that the hypothesis h star that is being output by a learning algorithm has an in-sample error and outer-sample error that are more than epsilon apart, so they're not close to each other. The chance that this happens is small. In particular, it goes down exponentially fast with n, and then you multiply in front of it with this growth function evaluated at 2 endpoints. Okay. Now, we also saw a couple of examples of different hypothesis sets in the last video where we bounded the growth function and got an exact formula. In general, it can be tedious and maybe hard or unrealistic to get a good exact formula for the growth function. But as we also remarked in the previous video, all we really need in order to use this generalization bound is just that we have a good upper bound on the growth function. And what we'll see in this video is a very important technique for obtaining such upper bounds. Okay, so to define this technique, I'm going to introduce a notion called shattering. Okay, so this shattering is some step towards bounding the growth function. Okay, so in general, we say that if we have k training examples like the 4 that we see here, and we have a hypothesis set h, then we say that these k examples are shattered by the hypothesis set if you can generate all possible labelings of them, so all the 2 to the k different dichotomies, right? So if there are 2 classes, there's 2 to the k different dichotomies, right? You can assign each one of them either red or blue, -1, +1. And if there's k points, there's 2 to the k different dichotomies. And if you can generate all of them, then we say that these k examples are shattered by h. Okay. So let's try to see an example of a hypothesis set that can shatter these 4 points. Well, the points here, they have 2 features, right? So the 2-dimensional points. And the hypothesis set that we're going to look at is the set of all axis-aligned rectangles. So a rectangle, an axis-aligned rectangle, we say that if I have such a hypothesis, I'm saying everything that lies inside the rectangle, I'm going to classify as red, and everything that lies outside the rectangle, I'm going to classify as blue. Right? It's kind of like a version of intervals in 2D. So we want to check that if this is our hypothesis set, we can choose any rectangles as our hypothesis, as our way of assigning labels. -1 if you're inside the rectangle, +1 if you're outside the rectangle, red or blue. Then you can actually shatter these 4 points. Right. So first of all, right, we have to be able to generate the dichotomy that assigns blue to all the points, or that actually meaning that we must have a rectangle that does not contain any of them. And this is an example here. Now, we also have to generate all the dichotomies where just a single point is colored red. So this would be these 4 rectangles, right? So we have to show that all of them exist. And we can see here in the picture, we can actually come up with a rectangle that contains just a single point. And we can do that for all the different 4 points on this picture. Okay. Next, we have to check that we can generate all rectangles that contain precisely 2 of the points. So as you can see here, right, I tried to draw all of them, right? We have a large gray rectangle here that contains the rightmost and the leftmost point. We have another gray rectangle here in the middle that contains the topmost and the bottommost point. We have a red rectangle here that contains the 2 bottom points. We have a blue rectangle that contains the 2 right points. We have a green rectangle that contains the 2 top points. And we have a yellow rectangle that contains the 2 left points. Right? So we can actually, for every set of 2 of them, there is a rectangle containing precisely those 2. So we can also generate all the dichotomies that color exactly 2 of them red and 2 of them blue. Okay. So then we have to check that we can generate all dichotomies that color exactly 3 of them red, meaning that we should have a rectangle for every subset of exactly 3 of the points. There should be a rectangle containing those 3 and no others. So they are here, right? So you can see here there's a yellow rectangle that contains every one but the leftmost. It's a green rectangle that contains every one but the topmost. There's a red rectangle that contains every one but the rightmost. And finally, there's a blue rectangle that contains every one but the bottommost point. So indeed, we can again generate all the possible dichotomies that have exactly 3 of these points inside the rectangle. And finally, we need to check that we can generate the dichotomy that has all the points colored red, meaning all of them are inside the rectangle. And we can do this using this rectangle here. All right, so what we've seen here is that this set of points, these 4 points, are actually shattered by the hypothesis set H containing all the hypotheses corresponding to an axis-aligned rectangle. Now, here's another set of 4 points. And for this set of 4 points, if we still look at the same hypothesis set, then we quickly see, right, that it's not possible to create this dichotomy here, right? We cannot create a dichotomy where the outer 4 points are inside the same rectangle, but the inner point is not. As you can see, if you try to draw any rectangle that's axis aligned and contains the outer 3 points, sorry, it will also contain the blue point in the middle, right? So this is a dichotomy we cannot create. So these 4 points are not shattered by H. Okay, so that's the difference, right? If we can generate all the 2 to the k dichotomies, then we say that these points or samples are shattered by H. Okay, so now with this definition of shattering, we can define what we call a breakpoint. So we say that this hypothesis set H, for instance, the axis-aligned rectangles, we say that if there does not exist a set of k samples, okay, so we cannot find k different examples that can be shattered by H, then k is a breakpoint for H. So let's have a look, right? So for instance, this set here with the axis-aligned rectangles, we saw that here 2 different data sets with 4 points. And this is not going to be a breakpoint, right? Because we have the left example here. So there are actually 4 points that can be shattered. And the definition of a breakpoint says that there must be no data set of k samples that can be shattered. So it doesn't matter that there's some sets of k points that you cannot shatter. As long as there's at least one that you can shatter, then you don't have a breakpoint. Right? So the breakpoint is the first number of points you can have where it's not possible to shatter any point set or set of k samples, right? So then it's a breakpoint. So 4 is not a breakpoint, which you can see here in the left example, because there are examples of 4 points that can be shattered by this hypothesis set H. Okay. You can, of course, ask by 5, and this is like a fairly easy exercise to prove that actually 5 is a breakpoint for axis-aligned rectangles in 2D. So it's not possible to find 5 points in the plane such that with axis-aligned rectangles, you can create all possible dichotomies, right? So for any subset of the points, you can find a rectangle that contains exactly those points and none of the rest. So 5 is actually a breakpoint for axis-aligned rectangles, but 4 is not, as you can see here on the left example, because there is actually a set of 4 points that can be shattered by this hypothesis. Okay, so maybe let's also go back to these examples that we saw in the previous video. So for instance, the positive rays. So we can start by asking, is 1 a breakpoint? So does it exist? Is it possible to find a single point where we can create all dichotomies, right? So there are 2 different dichotomies. If I have just a single point, right? Either I have the dichotomy where I color blue, or I have the dichotomy where I color red. And let's see that the positive rays, the hypothesis set of positive rays, can generate both dichotomies. So if you see here on the left, if you want to create the dichotomy that colors the point blue, then the point should not be inside the positive ray. So we can just take the ray that starts somewhere after the point. And indeed, it's possible to color this blue. And similarly, we can also create the dichotomy that colors it red. You just let the positive ray start before the point. So 1 is not a breakpoint, right? Because it is actually possible to shatter 1 point. So what about 2 points, right? So let's have a look. So if I have 2 points, right, I can always order them on the line. And so it will look something like this. And then we have to check, is it always possible to create all of these 4 dichotomies, right? This is so is it possible to shatter them? If it should be possible to shatter them, we must be able to create all these dichotomies. So let's start with the first one, right? Can we create a dichotomy that colors them all blue? And yes, this is easy, right? We just have a positive ray that starts after the last point. Similarly, here we can create a dichotomy that colors them all red. Oh, sorry, take this one first. Can we create a dichotomy that colors the rightmost red and the leftmost blue? And we can, right? We just create an interval that starts, a positive ray that starts somewhere in between. So this one we can create. We could also create this one down here where we color all of them red by just starting before it. And now the last one here is, can we create a dichotomy that colors the first one red and the last one blue? And this is not possible using a positive ray, right? Because if a positive ray includes the first point, it will have to include the last point. So this is not possible. And this argument holds for any choice of 2 points, right? Regardless of how you place 2 points, it's never possible to create the dichotomy that has the leftmost point red and the rightmost point blue using a positive ray. So 2 is a breakpoint for positive rays. Okay. Now we also have the intervals example. Right, so let's see, is 2 a breakpoint for intervals? And the first 3 we already kind of went through, right? Because we can always, you know, with an interval, we can always create a positive ray by just by extending it, the interval towards plus infinity. The question is, can an interval generate this last dichotomy here that we couldn't create with a positive ray? And indeed, this is possible with an interval, right? We just create the interval that just goes from before the point to after the point. Okay, so here the arrow just means from the left point of the arrow to the right point of the arrow. So indeed, 2 is not a breakpoint for intervals. And you can ask, okay, so then we can check, well, is it possible to create all dichotomies, all labelings of 3 points? So there's all these 2 to the 3 different labelings of dichotomies. We have to check whether we can create all of them, right? So maybe we can just go through them one at a time. First, we can check, can we create the dichotomy that colors them all blue? Right? This is easy. We can just create an interval that starts before all of them. We can also create this dichotomy where we color the rightmost red and none of the others. We can create this one, just containing an interval containing just that point. Similarly here and here, we can just contain those 2 points. We contain all of the points. And then we have this last dichotomy down here, right, where the 2 outer points are colored red and the inner point is colored blue. And what we see here is that this is not possible to create this dichotomy using an interval. And this is true for all sets of 3 points, right? Regardless of which 3 points you give me, if I order them on the line, then it's not possible to create the dichotomy that color the 2 outermost points red and the innermost point blue. And this holds for all sets of 3 examples, that this is not possible. So 3 is a breakpoint for intervals. Now we can take the last example that we saw last time, the convex sets in 2D. And we saw this example that it's actually possible to place these points on a circle. And if we do so, if we place k examples on a circle, then we can create all 2 to the k different dichotomies, right? Because we can just create the convex set that has just the red points, the ones we want to be red, as the vertices. And then it's just a convex polygon that contains just those vertices. And really, right, the definition of a breakpoint says that there can be no data set of k samples that can be shattered by h. But this set of for every k, you can always put k points on a circle and then you can shatter it. So which means that it doesn't have any breakpoints. The convex sets in 2D does not have breakpoints. Okay. So with this definition of breakpoints and shattering, we finally get to the definition of VCDimension, probably one of the most important definitions in learning theory. So the VCDimension is named after its inventors, authors. So the VCDimension of a hypothesis set is defined as the D such that D is 1 less than the smallest breakpoint. Okay, so let's say that again, right? If K is the smallest breakpoint for the hypothesis set, then the VCDimension is 1 less, K minus 1. So maybe in another set it differently, and maybe a more intuitive way, is that D is the largest integer such that there is a data set of size D that you can shatter, right? So this means that the integer 1 up would be a breakpoint because D is the largest integer where you can shatter a data set. So in the next, at D plus 1, you cannot shatter it, any data set at all. So D plus 1 must be a breakpoint. D is the largest place where you don't have a breakpoint. Okay, so that's the VCDimension. So it's the largest integer such that you can find a data set of size D that you can shatter using the hypothesis set H. That's the VCDimension. Okay, so let's look at our examples again, right? So what are the VC dimensions? So with the positive rays, right, the VC dimension is 1 because we saw, well, with 1 point, it was possible to create both dichotomies, but it was not possible to find 2 examples. There was no set of 2 points where you can create the dichotomy where the interval assigns red to the first point, the leftmost point, and blue to the rightmost point. So it cannot shatter a set of 2 points. So the VC dimension is 1 here. For the intervals, the VC dimension is 2 because we saw we can create all dichotomies. There exists a set of 2 points that you can create all dichotomies on, but there does not exist a set of 3 points where you can create all dichotomies. So here the VC dimension is 2. I guess even though it's not put here on the slides, we saw these axis-aligned rectangles, right? And we saw that with 4 points, we could actually find 4 points where we can create all 2 to the 4 dichotomies. So we can shatter a set of 4 points. And then we said that it was left as really an exercise to show that it's not possible to shatter any set of 5 points. So the VC dimension for axis-aligned rectangles would be 4. Now, and finally, for these convex sets, we say if there's no breakpoint, then we define the VC dimension to be infinite. Okay, so that's the VC dimension, right? The VC dimension of a hypothesis set is the D, such that D is the largest size of a set of samples that you can actually shatter. Okay. Good. So now the reason for introducing this VC dimension is that it actually gives a bound on the growth function, right? So it's a very nice way of bounding the growth function. In particular, it can be shown that if I have a hypothesis set of VC dimension D, then the growth function is no more than n to the D plus 1. And this can be tightened a little bit, but not by much, right? This is basically the way it grows, as in the worst case. So which means that we can always take this bound that we had before, right? We saw this generalization bound saying that the in-sample error and out-of-sample error are close. The chance that they're far apart is small. And so the chance that they're more than epsilon apart is at most. This is where we have the growth function times something exponentially small in epsilon squared n. And if we have a bound on the VC dimension of H, we get a bound on the growth function. So we can just plug that in, right? So we get a bound on the growth function of n to the D plus 1. And then if I know my VC dimension is bounded by D, I can just plug in this as the growth function here, right? So I take this n to the D plus 1. I plug in 2n as I have here in the bound. So I get 2n to the D plus 1. It's basically 2n to the D, right? The plus 1 is a almost irrelevant term. But then you get a bound like this one. So now, as soon as I have a bound on the VC dimension, I know that it's bounded. Then I can immediately get these generalization bounds for a learning algorithm that outputs a hypothesis from this hypothesis set. So in particular, we know that with if I draw a random training data set, then the chance that the in-sample error and out-of-sample error of the hypothesis that my learning algorithm outputs, the chance that these are more than epsilon apart is no more than this expression here. There's an 8, 2n to the D plus 1, and then this e to the minus epsilon squared n over 8. So I immediately get bound, right? So I can just take my examples, right, with the positive rays. I know the VC dimension is 1, so I can just plug in 1 here, and I get a bound immediately, right? The intervals, the VC dimension was 2, so I can just plug that in here. And for convex sets, it's meaningless. I could also, if I took the axis-aligned rectangles in 2D, I can just plug in a 4 here. So this VC dimension at least seems easier to work with than this growth function does if you work with it directly. Here you just have to argue that it's not possible to shatter a set of size, right, for some size D, and then you get bounds. Right? You just have to give an upper bound on the VC dimension, then you get an upper bound on the growth function. Okay, and now if we just look a little bit at this formula and just see what do we get out of it. So the observation is that if this VC dimension D, right, if it doesn't grow with the data set size, right, if D is a fixed constant, like it is for all these examples that we saw earlier, then this n to the D factor, right, that you have here in front, it grows polynomially fast with n, whereas the other term here is going down exponentially fast with n, which means basically if as soon as I'm using a hypothesis set with a bounded VC dimension, then I know as soon as I have enough data, given enough data, then I'm starting to get guarantees on the closeness of the in-sample error and out-of-sample error, right? So basically, if the VC dimension is bounded, then given enough data, the in-sample error and out-of-sample error will be close with very high probability. So that's a really good guideline or a good way of being confident that you can use this hypothesis set to learn. As soon as I know it has a bounded VC dimension, then as long as I have enough data, then eventually the in-sample error and out-of-sample error are going to be close with high probability. Good. So the VC dimension is really a tool for making it easier to get upper bounds on these generalizations. And it's a little bit easier to bound it than getting an exact formula for the growth function. And it's also a very nice definition and a concrete way of assigning like a complexity score, if you will, of a hypothesis set, talking about how complicated is this hypothesis set, right? What is its VC dimension? And if you can see also here, right, if you look at the bound, right, an important conclusion is that, well, if I use a less complicated hypothesis set, even if we're looking at infinite hypothesis set, one that has a smaller VC dimension, then we can be more certain that the in-sample error and out-of-sample error are going to be close. Right, so this is a good guideline. And then maybe let me just finish off by this plot here, like this imaginative plot. So what I've tried to draw here is that out here on the x-axis, we have the VC dimension of the hypothesis set we're using for a learning problem, which means in some sense, like the model complexity grows. So ignore the y-axis for the model complexity, but somehow as you go out here on the x-axis, you're kind of using a more and more complicated model. Now, if I have a more and more complicated model, one with more and more parameters I can fine tune, then you would also expect that on the training data, you can get a smaller and smaller in-sample error, right? Because you have more power to fit the training data. You have more parameters you can fine tune in order to make good predictions on your training data. So you would expect that as you increase the VC dimension of the hypothesis that you're using, then in general, the in-sample error will keep decreasing, right? You'll get a lower and lower in-sample error. Now, the interesting thing is that the gap between the in-sample error and out-of-sample error in the beginning, they're really close. But as you go further out, you risk that there's a larger and larger gap between the in-sample error and out-of-sample error, which means basically that here in the beginning, as you use a more and more complicated hypothesis set, because they're close to each other, the in-sample error goes down, and then since they're close, so does the outer-sample error, right? So the in-sample error kind of pulls the outer-sample error down with it. But eventually, the gain in the in-sample error that you get from using a more and more complicated model is not paid for by the gap between, because the gap between the in-sample error and outer-sample error just gets bigger and might get bigger and bigger. So this is in some sense what we call overfitting, that we'll return to much later again. But the basic idea is that in the beginning, it pays off to use a more and more complicated model. But then eventually, when you don't really have enough data to make sure that the in-sample error and out-sample error are close, then maybe this gap starts growing again. And intuitively, you want to choose a model somewhere here in the sweet spot that is complicated enough that you've driven the in-sample error far enough down, but not so complicated that the gap between the in-sample error and out-sample error has grown too much. Right? So this is the basic idea in learning, right? You want to choose a hypothesis set that's just right compared to how much training data you have available. Okay, so let us end on that note.